Next we had the question, we have a basis 1, 1, 0, negative 1. Okay, and maybe it would be good to write that down someplace, although I don't really have a good place. I'll write it down here. Use a script B for the basis. I don't know if you can even read that. And that basis is going to be 1, 1, 0, negative 1. Now, what the question I posed is, what combination of these basis vectors will give you the standard basis for R2? Of course, these are obviously vectors in R2. Okay, well, the basis vectors, the standard basis of R2 is just 1, 0, 0, 1, right? So what combination of these vectors will give you the first basis vector? Okay, what combination of these basis vectors will give you the first standard basis vector? Well, we write that as an equation. C1 times the first of these basis vectors plus C2 times the second equals our first standard basis vector. And then we ask the same thing of our second standard basis vector. We'll use D1 and D2 for the multiples of our basis B that add up to that. Okay, so this equation says what linear combination of our new basis vectors yield 1, 0 of the standard basis, and here's a combination that yields 0, 1 of the standard basis. Okay, we can write each of these equations as a matrix equation, and the matrix equations are actually going to have the same matrix. If we write this system in matrix form, you can verify easily that this is what it's going to look like. Okay, that this system gives us this equation. And similarly, that this system is equivalent to this matrix equation, or vector equation if you wish. Okay, we have the same matrix both times because, of course, we're using the same basis vectors. You know, the vectors from this basis. Here, we're going to get those basis vectors in our columns. To solve these equations, all we have to do is invert this matrix and then multiply by this basis vector and this basis vector. We'll get our linear combination. We invert the matrix just by writing an augmented matrix with the identity, reducing to the identity, and getting our inverse matrix. Turns out that our inverse matrix is the same as our original matrix. So that won't always happen, but in this case it did. Okay, so the solution to this equation is to multiply both sides by the inverse matrix. And again, the inverse matrix is the same as this matrix. So when that happens, we get our solution C1, C2. That gives us 1, 1. Meaning that if we add 1 times this plus 1 times this, we get this. Well, clearly, if we add 1, 1 to 0, negative 1, we do get 1, 0, don't we? And solving for D1, D2, so we see what combination we need here. Okay, we get 0, negative 1. We don't add any of this, and we just do negative 1 times this, because negative 1 times this will give us this. Negative 1 times negative 1 is 1. Negative 1 times 0 is 0. Okay, so we've solved that. Now we can actually do more. We can actually solve this by reducing an augmented matrix. A matrix, this matrix augmented by the matrix of these two columns. When we do that, what we get is going to look very, very familiar. Okay, I'm not going to do it. We'll go on with that. This is where we kind of ended up, and we'll see how we can combine this. And usually we'll want to be writing, or very often at least, we're going to want to be writing a combination of our standard basis vectors equal to each of are new basis vectors, each of the vectors in the basis B. And we're going to get a matrix out of that, and in a very simple way we'll be able to figure how to transform from a vector representation in the standard basis to vector representation in this basis, or vice versa. So that's where we're heading with this. We're almost there. We didn't get quite that far, and we'll be starting out with this in our next class.